thank you all for being here. It's a pleasure to come to Ljubljana for the first time. Hopefully, we'll have a week of a lot of activities and a lot of meetings as well, unfortunately. But I'll be happy to explain a little bit what we did in this project that we finished last year. So this project is called FlowPhotoChem. We were 15 partners across Europe and Africa. And the idea was to use just CO2, water, and sunlight to produce ethylene. Yeah, so this project is based on the fact that so it was funded through the European Commission, and in particular the Industrial Leadership Program. And the reason was that the European chemicals industry, although it provides a huge amount of jobs to the European workforce, it provides also about 500 billion in sales, but it's also considered one of the most highly polluting industries. And to consider that we have to reach the climate targets for Europe by 2030, going down 40% in CO2 emissions, and by 2050 as the European target to become a climate neutral continent, we have to basically follow the Sustainable Development Goals. And in FlowPhotoChem, we were targeting basically these three, SDG 7, 12, and 13, in particular 7 on the affordable and clean energy production. And the idea, of course, was to produce more sustainable manufacturing, to reduce from the resilience that we have on fossil fuels, and also to reinforce the cooperation between EU and Africa, given that we are targeting production of chemicals using basically solar energy mostly. Okay, and the idea is that when you look at the chemical industry and how to green up the chemical industry, there are basically 3 steps that we can follow. And this could be kind of divided in the short, the medium, and the long-term solutions. In the short term, and that has been done already for 15, 20 years, it is related to process and energy optimization. But the problem is that the reduction of CO2 emissions, this is quite low. The advantage, of course, for the industries is that it has lower cost and lower risk as well. In terms of medium-term solution, and a lot of industries are working on this already, will be to replace fossil fuel energy generation by renewable energy. So, of course, this has a higher CO2 reduction potential, but also higher cost and higher risk depending on the type of industry. On top, and the high cost, high risk, but high potential for CO2 reduction is basically to incorporate as part of the chemical industry these CO2 reduced breakthrough technologies, or what are called also negative CO2 technologies. And an example that we have been using for FlowPhotoChem is basically looking at what we call these platform chemicals. Okay, so we have this methanol, ethylene, propylene, all these platform chemicals that are used for production of from plastics to agriculture use to many, many other uses. And of course, based on the traditional fossil fuels-based industry, all this is coming from petrol and gas. If we shift to like an intermediate solution coming to the bio-based chemical industry, we can use biomass and some other sources that end up reducing the amount of CO2 that you are delivering to reach the same targets, these platform chemicals. But of course, what we want to do is to achieve these platform chemicals in a way that we reach them using these carbon negative technologies. So what we have done in FlowPhotoChem, and I wanted to put this into the kind of the state of the art and the background on where we are in terms of these direct solar energy conversion technologies. You might know that a couple of years ago, there was this prize from the European Innovation Council on artificial photosynthesis. And there were 3 teams that were selected as finalists, and they had to go to Italy for a week to set up their own reactors, their own production, and they had to demonstrate that by using just sunlight, water, and CO2, they were able to produce a carbon-based fuel. Okay? Out of the 3 teams, the winner was the University of Tokyo, and they were basically producing these photocatalytic sheets. I think they have a price. So these photocatalytic sheets to produce hydrogen and oxygen. They were separating the hydrogen, and then in a methanation reaction, they were converting the hydrogen and CO2 to methane. And then basically they were using this gaseous fuel to demonstrate the production of this solar fuel. Okay? So just to give you some numbers and remember some of these numbers, this demonstration in Italy, so that was like real for a couple of days in Italy. They had about 12 square meters of photovoltaic sheets for water splitting. This was kind of a small part of the real demonstration that they have in Japan, where they have 300 square meters of photovoltaic sheets that have been running for about almost 2 years. And I just recently knew that they are now building up 30,000 square meters of these photovoltaic sheets in Japan for a next step, like pre-commercial. Yep. So some of the numbers. This, and remember that this is the winner of the EAC prize, 5 million euro for the winner. Average solar to energy to solar to hydrogen conversion, about 0.5%. The total volume in 3 days, about 640 liters of hydrogen. Yeah? And of course, this was for the 12 square meters demonstration in the price, but just remember some of these numbers. Yeah, so what we wanted to do in FlowPhotoChem was kind of a bit ambitious, because we were not only targeting one type of technology, but we were targeting 3. And the idea, as I mentioned, was basically to use sunlight, water, and CO2 to end up producing ethylene. The way that we were doing this is by combining 3 types of reactors, 3 types of technologies. A photoelectrochemical reactor that was taking up water and sunlight and producing hydrogen. A photothermal catalytic reactor where we were doing CO2 hydrogenation to CO, and a CO electrolyzer to go from CO to ethylene. Yeah? And the idea was not only to design and construct these individual reactors at the lab scale, but also scaling them up and then bringing the 3 reactors in the same place and connecting them in series to produce ethylene with just the CO2, water, and sunlight. Yeah, so across the 4.5 years of the project, we have worked quite a bit on development of materials, membranes, and reactors. Okay, so these are some of the papers that we have been publishing in each of the individual reactors. But what we wanted to show today is more the results of the combination of the different reactors in the final demonstration. Yeah, so just to show you where we were, okay? This is the work from Professor Sophia Hausener at EPFL, where they have been working for several years now in these concentrated photoelectrochemical reactors. Okay, what they have, and that's in the campus in EPFL, is one of these concentrator dishes, outdoor, and they concentrate light to the focal point that you have here, where we have a photoelectrochemical reactor. Yep. This reactor has been running, or was running for 40 continuous days at EPFL, and that was in 2022. And what we can see here is that we have a perfect match between the solar input, that's what you have on the top graph, okay, where you can see the solar irradiance that you have every day, and of course the days that are a bit cloudy, you have less. The lines that you have here, these are weekends, that because of health and safety, this was shut down, and it was only in operation during the weekdays. And it matches perfectly with the plot on the bottom, where we have the actual hydrogen production across these 40 days. Okay, so the cumulative hydrogen production in these 40 days was also measured, and it equaled about 10 kilograms of solar hydrogen. And remember that this is not connected to grid, it's not connected to anywhere. Okay, so it's a solar dish with a photochemical reactor, water input, oxygen, hydrogen produced. The total number in 40 days, 110,000 liters. Okay, so that's 3 orders of magnitude more than the 3-day demonstration from the prize that was won by the University of Tokyo. And of course, at the same time as you are producing hydrogen, you're also producing oxygen, in this case 80 kilos. And because of the high intensity of the concentration that we have in the system, that's about 600 to 700 suns. So you can also recover the thermal heat that is captured as part of the system. And this equals to about 3,000 kilowatt hour of thermal heat that you can use for another application that you can valorize as well at the same time as you are producing the hydrogen and the oxygen. And as part of this first reactor, one of the kind of challenges that we were facing in the production of this system is that this is combining basically a photovoltaic component and the type of photovoltaic component that is used in these systems at such high concentration are basically photovoltaic solar panels that are used in space. Okay, these 3-5 semiconductors that they are very expensive, and you needed basically some sort of an electrolyzer or an electrochemical component that can match the high current that you're getting out of this high concentration. Okay, so in order to do that, the first choice that we used as part of the project was basically use the more commercially available proton exchange membrane electrolyzer. But of course, as part of the project, what we wanted to do is to move away from a PEM type of electrolyzer to an AEM type of electrolyzer so that we could get rid of iridium, the ruthenium, and the platinum, as Chile has mentioned before. Okay, so as part of our work, and that's some work that we have done in my team in Galway with Hanka and Simon, was basically to try to develop oxygen evolution catalysts that are compatible with operation at high current density. Okay, so we have selected these cobalt-based systems, cobalt oxide, and with a simple kind of type of synthesis so that we can scale up to gram scale production easily, we have prepared different types of morphologies, okay, sheets, flowers, and cubes. And out of them, we select the ones that are the most promising for the OBR at high current densities. Okay, because of that, we also know that just cobalt oxide is not a very, very good catalyst at these high concentration, high current densities. So apart from selecting basically the nanosheet structure as the one that has the most promising results, we also, from electrochemical characterization, but we also look at the fact that by adding iron, that is also well known in the case of nickel type systems, the addition of iron as a dopant into these systems enhances the catalytic activity for these metal oxides. Okay, the problem is that usually you have a lot of iron, and what happens is that when you add too much iron, you start producing a separate phase. You have some cobalt oxide or cobalt oxyhydroxide form under the catalytic conditions, but also some iron oxyhydroxide. And the formation of this iron oxyhydroxide is detrimental for the activity for OBR because you are starting to generate this electrically insulating phase that will increase the resistance of your electrode. And so what we did was basically look at how low can we go in terms of iron doping into a cobalt oxide structure, to just keeping up the spinel structure that you have in the cobalt oxide, but trying to see how much would be this solid solubility of adding iron into this cobalt oxide. And we saw that up to 7.5%, you have no change, you still have the cobalt oxide phase. At 10% of iron, you start to see the formation of this secondary phase. That's what we don't want. Okay, so we have done the electron microscopic characterization and making sure that we have this sheet stripe of structure. And also we see that it is not only a sheet structure, but is also a porous structure that allows us to have this higher activity for these systems. We have also done some simple deposition of this powder catalyst into nickel foams and nickel felts to see the effect of this low doping concentration, and also to check basically the electrochemistry properties, the Tafel plots, to see which of the different combinations of iron and cobalt was giving the best performance at these high current densities. We have also tested the activity at different temperatures so that we can decide which is the best at the higher temperatures that are usually used in a single cell and ion exchange membrane electrolyzer. And we saw that this 5% of iron doping in the cobalt oxide was performing the best in terms of activity and stability under these conditions. Yes, so the next step, and that was also worked on by Hanka in collaboration with TU Berlin, with Fabio here in the audience, was that we could incorporate this as an OER catalyst, as an anode catalyst for an AEM system, and do the testing in completely PGM-free, so no iron, no ruthenium, no iridium, no platinum in the system, just iron and cobalt for both the anode and the cathode. And we can see that we can reach current densities, high current densities at reasonably low potentials. And we can also see that the stability of the system, and you can see here the stability of the system, this all PGM-free single cell, it is also very good and consistent with the fact that we can then potentially incorporate this catalyst as part of the full photoelectrochemical reactor. Yeah, we can see also after long-term experiments, after 100 hours of experiments, that the performance of this system behaves exactly the same. Yeah, so moving away from the first type of reactor, this photoelectrochemical reactor, we can focus now on the second type, where we do the CO2 hydrogenation to CO. And we have been working on many types of different materials. Okay? We have been working on 2D MOFs, some COFs, some hydroxyapatites. But the one that showed the best performance, not only in terms of activity, but also stability, was still this ruthenium strontium titanate. Okay? One of the things that we have seen in this system is that the production targets, so the chemicals that we are getting out of the CO2 hydrogenation, depend quite a bit on the irradiance on the reactor. Okay, so the more higher intensity that we can see, okay, so we go from about 40 to 98 SANs, we can see that the fraction of CO versus methane increases quite a bit. So at low photon flux, we have mostly methane formation, so CO2 hydrogenation to methane. At higher solar intensity, you have mostly CO. And the most important thing is that we wanted to have production rates that can match what we are getting out of the photoelectrochemical reactor. Okay, so we are not anymore in the micromole per hour production, but now in the millimole per gram per hour of catalyst. Okay? So we have also then designed not only the materials, but also these scale-up reactors. That's about 100 square centimeters of active illumination area, and we can produce now this mostly CO in this system. The third reactor was the CO electrolyzer. And of course, when we started this project, there were a couple of examples in the literature of CO2 electrolysis, CO2 electrolyzers, mostly in the lab scale, but there was nothing on CO electrolysis. Okay, so we had to come up with new strategies to basically circumvent the fact that CO has very different solubility in water compared to CO2. And this was done basically mainly by the partners in Szeged University and from Helmholtz Zentrum, Berlin, by Professor Matt Meyer and Csaba Janaki. Yep. So we have tested small-scale reactor. We have also been working on different types of reactors, from microfluidics to a hybrid zero gap to a full zero gap, to see the scalability, the effect of different flow patterns, the effect of the different conditions and fits. And the final objective was basically to have something that could be scalable, and not only in a single cell, but in a stack, a CO electrolyzer stack, to produce ethylene. Okay, so we have results from the different systems at high current densities as well. Remember that we need to match with what we have from the two previous reactors. And out of this, we selected the zero gap as the preference system. And the scale-up of this device was done by the startup company coming out from Szeged University, eChemicals, also based in Hungary. And we were able to go from 100 square centimeters to 300 square centimeters 3-cell stack with very good performance. You can see that we have voltages of about 2.7, 2.6 volts with, and that's even more important, Faraday efficiencies towards ethylene with over 60%. Okay, so we can see that now we have the photoelectrochemical reactor scale up, the photochemical reactor scale up, and the electrochemical reactor scale up, and ready to basically be put together. Yeah. One of the challenges when you have these multi-partner projects in different countries and you want to do a demonstration of all the different technologies in one single place is that you need to move all the reactors into one single point. No? So what we had done here was that the photoelectrochemical reactor developed in Switzerland, the photochemical reactor developed in Spain, and the electrochemical reactor developed in Hungary. The 3 reactors were sent to Germany, to DLR, where we were having basically the demonstration of the integrated device. Of course, one of the things that we wanted to do is to have a better control of all the system. So instead of using outdoor illumination, we used indoor solar simulators that are available in DLR. And we were basically testing the combination of the 3 reactors put in series. At a small scale, what we have done as well is to check which other combinations of reactors we can use to reach ethylene production. And even though path B seemed quite interesting, where we could do directly CO2 hydrogenation to ethylene, this was very, very complicated to reach the production target that we had. But path C was possible. Okay, so what we did was to develop a photoelectrochemical reactor where the electrochemical component was not doing water splitting, but was doing CO2 reduction to CO. And then feed the CO gas directly to the electrolyzer to produce ethylene. Okay, so this was done. We were able to combine these 2 reactors at EPFL in their own indoor solar simulator, and we were able to reach a solar to ethylene efficiency of about 3% in this short-term demonstration and also smaller scale. Yeah? So in terms of the integration, so we have the 3 reactors combined up together and bringing all the control, so that's, don't be scared, so that's the whole control system of the engineering of the integration of the 3 reactors. Okay, you can see here photoelectrochemical reactor, photochemical, and electrochemical reactor with all the pumps, mass flow controllers, and also the liquid and gas ports for the collection of every single liquid and gaseous product that comes out of every single reactor. Another issue that we had is that, of course, in the photoelectrochemical reactor, one of the challenges that we had was that the single pass conversion, okay, so how much CO2 is converted to CO, was quite small, was about 33%, so basically the theoretical maximum for a reverse water gas shift, which means that you still have a lot of CO2 in the output of the photochemical reactor. If everything that we designed in the electrochemical reactor was for CO2 feeds, we needed to somehow remove the CO2 out of this gaseous output. Okay, so in some place in the system, I think somewhere here, what we had is a unit for CO2 capture, so that everything that is coming inside of the electrochemical reactor is only a mixture of CO and some hydrogen unreacted that you have from the photochemical reactor. Yeah, so this is how it looks like. So we have the 3 reactors, the photoelectrochemical reactor here, the photochemical reactor here, and the electrochemical reactor in a table. Okay, you can see here. And all this is illuminated by these xenon lamps that you have here. Okay, so in DLR, they have this system where they can activate and focus each of these xenon lamps in different directions. Okay, so what we had is that about 8 of these lamps were focusing to the photoelectrochemical reactor, and 2 or 3 of these lamps were focusing on the photochemical reactor, because one was operating at 500, 600 suns, the other was operated at 80 suns, more or less, okay, to basically match the production rates of the different reactors. So this was done, this was completed last year in June, and we had about 14 hours of operation of the 3 reactors functioning in series and producing ethylene. Okay, you can see here a real image of the system in production. And to show you that we are not just inventing and having this and not showing the results, we have also all the data from every single reactor, okay, out of production, coming off oxygen, hydrogen from the first reactor, the CO and unreacted CO2, hydrogen, and also some methane coming from the second reactor, and from the electrochemical reactor, that we have also the ethylene production. Okay, so overall, what we have achieved in this continuous operation of the 3 systems is a solar to ethylene conversion of about 0.67%. Yeah. We have If you consider other C2 plus products, we can go up to 1%. If we consider all the gaseous and liquid products of the system, it goes up to 9.6%. Okay, so that's real solar to chemical efficiency of 9% more or less in this 14 hours operation that was split into 3 days. Okay? Because not only we have done the experimental setup, but we have also done kind of the modeling of the 3 different reactors and the combination of all of them. What we have been doing as well is to see which were the weakest points and how to improve the efficiency. And we can see that basically we have a very good kind of a pathway or a roadmap to basically move from this like 0.67% efficiency for ethylene alone to something that is close to a 7% efficiency to ethylene. Okay, because as part of this, we had also some other issues, as you can imagine, moving reactors, some scratches, some bricks of the quartz glass that basically reduced quite a bit the performance of some of the reactors that we had in hand. With that, I think that I'm okay with time. So thank you for listening. That's some of the team in FlowPhotoChem. As 15 partners, we were almost 70 people working for 4.5 years to achieve these, hopefully, nice results that you have seen in this presentation. So thank you. And if you have any questions, just happy to answer. And we have also a video that you can access through the website to summarize basically the results that we have done in this project. Thank you.